Let us now consider an example where Alice and Bob don't have the maximally entangled state. Instead, they will have another state. This state will be less entangled, and we will see a smaller winning probability. So let's remember what the winning probability of our game was. I've written it again here, where these are the correct answers for Bob according to the rules. This game is also known as the CHSH game. The state that Alice and Bob will use in the game is this one, which is a mixture between the maximally entangled state, with probability P, and in fact the maximally mixed state for both parties. This state has a name, namely it's called the Werner state. Let's see what is the probability that Alice and Bob win the game, given the state, as a function of P. To think about this, let's first observe that if I compute the probability of Alice and Bob getting some measurement outcomes, A and B, given questions X and Y, psi, A for Alice, tensor B for Bob, on the maximally entangled state, it looks like this. B for Bob. Again, I'm just using the fact that the trace is cyclic. So now, if we use the Werner state instead of the EPR pair, what we can plug in here is just rho AB. So with the Werner state, my probability of seeing A and B given X and Y is given by the trace of rho AB times these measurement operators. Y. So note that the trace is linear, so I can just write this as P times the probability on the maximally entangled state, namely this one, plus 1 minus P times the probability on the maximally mixed state. So if I think about what is the probability to win the game using the Werner state, it's easy to see that this is also equal to the probability of winning the game with the maximally entangled state, and I'll write this like this, plus 1 minus the probability to win the game using the maximally mixed state, and I'll write this like this. So this first term we already know. Namely, we know this winning probability, if we use the measurements, is half plus 1 over square root 2, which is roughly 0.85. Let's now compute what is the winning probability for the maximally mixed state. To compute this, note that the probability of seeing A and B given x and y on the maximally mixed state is the trace of the identity on A and B over 4 A, B, B, which is just 1 over 4 times the trace of these vectors, which is 1. So if we think now about the winning probability, all we have to do is count the number of terms. So 4 possible values of x and y, and for each of them we have 1 possible value of A. So in total, there's 8 possible combinations, x and y and A. So we don't need to worry about B, because B is completely determined once A, x and y are fixed. So this winning probability for the maximally entangled state, we keep the 1 over 4 from out here. And now I have 8 terms, which are like 1 over 4. So this is 1 over 4 times 2, or if you want, a half. So this gives us an overall winning probability of P times our original winning probability, and 1 minus P times a half. So you should go out and figure out for which values of P is this still larger than 3/4. This is an example of playing the CHSH game with a state that is not the maximally entangled state.